This is David Spear, Civil Engineering Instructor at Texas Tech University, reviewing a recent solid CE 3303 exam. First problem that we have is a bending stress and flexure formula problem. We have a channel C-shaped beam with a y-axis bending. The moment in this case is 25 kilonewton meters. And note that it's a y-axis bending. It's bending about the y-axis. We're given the moments of inertia about both axes. See if you can sort out which one to use. We've got Ix and Iy. And then we also have a centroid distance, x bar, which is shown on the drawing to be 44.2 millimeters. That should have been a hint as to what we're dealing with for giving you the y-axis, but also the x-axis is located by symmetry at the center of the shape. So, the first problem we want to know is the normal stress at point C. Okay, if we're dealing with flexure, we're dealing with the formula of sigma, the bending stress, which for us is going to be megapascals or kilopascals, is my over I, where m is the bending moment and I is the moment of inertia that the bending is about. So it's y-axis bending, therefore we're using Iy. And y is the distance from the neutral axis. So those are the important things that you need to sort out before you do the problem, because the math is really quite easy. Okay, so the first problem is determine the normal stress at point C. Okay, so we can look at this moment and we can see the way this moment is directed. It's tension on the right side and compression. Even though you weren't even really asked for this, you need to start developing the habit of looking for tension and compression. Anyway, I've got compression at point C, which is where that first problem is, on the right side, on the left side, excuse me, of the section caused by that moment. So it's really just kind of a matter of getting the units correct. The sigma at C is the moment, which is, it's going to be producing compression, so I'm going to show it as negative, 25 kilonewton meters. And I want to work in newtons and millimeters. So I'm going to multiply by 1,000 to get it into newtons. That's newtons per kilonewton. And then I'm going to multiply by 1,000 to get it into millimeters, which is millimeters per meter. So now I've got newtons and millimeters for my moment, 25 million. My y distance is the distance from the neutral axis. Well, the neutral axis is this y-axis, because that's what the bending is about. The bending is like that, about that y-axis. So the distance from the neutral axis to point C is that centroidal distance, 44.2. And then on the bottom I just need Iy, moment of inertia about the centroidal y-axis, which is 13.9, 10 to the 6th. That's millimeters to the 4th. On the top I have millimeters for that y-bar distance, or that x-bar distance. And the number works out to be, it's negative, but we don't even ask you for that, negative 79.5 megapascals. That's answer C. For the normal stress, bending normal stress at point E is this point right here. The numbers are still the same except for that x distance, or the distance from the neutral axis to point E. That is that distance right there, small little distance. I'm told that the web of this thing is 37 millimeters, So that y distance, or the distance from the neutral axis, just 44.2 minus 37. So sigma at E, very similar. I still have 25, and I still got compression on that side. 25,000 for units. My y distance, or that distance from the neutral axis, is 44.2 minus 37. That little distance, same I, 13.9, 10 to the 6th. And for this one I get negative 12.95 megapascals. And that is answer B. Okay, then I'm asked a partial credit question. It says, if the allowable normal stress at point D is 50 megapascals, determine the maximum moment on the channel. Well, I'll still use the same formula, just rearrange it. And so what I'm going to have is this point D. The thing that matters, one of the main things, is this distance from the neutral axis. I need to calculate that. But I can from this 120, the width of the flange of the channel, and just rearrange my equation. I have sigma is equal to my over I, therefore m is equal to sigma I over y. So my allowable bending stress is 50 megapascals, which is newtons per millimeters squared. I is that still, it's y-axis bending, so I'm dealing with IY, 13.9, 10 to the 6th. That's millimeters to the 4th. And that y distance, as I said, from the neutral axis to point D is 120 minus 44.2, excuse me. That's millimeters. I'm working in newtons and millimeters, so I get the answer is 9.17, 10 to the 6th. That's newton millimeters. And another way of putting it is 9.17 kilonewton meters, which kind of is consistent with my overall problem. I was given a moment of 25 kilonewton meters, and see what the stresses are. Well, they're the same magnitude, or kind of close to that 9.50 megapascals. So this answer makes sense to me.